In 1955, Emory W. Lane presented a relation between sediment load and hydraulic variables. This relation states the proportionality between the product of sediment discharge and particle size on the left-hand side and the product of water discharge and bottom slope on the right-hand side. At equilibrium, this relation holds. Under non-equilibrium conditions, when any of these variables changes, the relation indicates the direction of the changes which are necessary in one or more of the other variables to restore equilibrium. For instance, if the sediment load is decreased, equilibrium can be restored by decreasing the water discharge or the bottom slope, or by increasing the sediment size. The sediment discharge is the bed material load. It excludes the fine material load, or wash load, which is transported through the system largely without affecting the river hydraulics. This photo shows the effect of releasing sediment-free water from a dam. A reduction in sediment load caused a reduction in bottom slope downstream of the dam, triggering channel degradation exceeding 3 meters. This photo shows the effect of a sediment retention dam in a small creek. A reduction in sediment load downstream of the dam caused the stream to erode to bedrock about 3 meters within a short time span. Thus, as the Lane relation predicts, decreases in sediment load downstream of a dam result in hungry water. Hungry water leads to channel degradation until a new equilibrium is reached. The Lane relation can be expressed in dimensionless form by using suitable hydraulic and sediment transport relations. 1. The dimensionless Chezy friction formula. 2. The Colby sediment transport formula. And 3. The Strickler relation for Manning's N. The following derivations are strictly applicable to hydraulically wide channels. The dimensionless Chezy formula is the Colby sediment transport formula states the proportionality between unit width sediment discharge and mean velocity. Where ρ is the mass density of the water, and K sub 1 and m are coefficient and exponent, respectively, of the power function. In general, the exponent m varies between 3 and 7. Values in the lower range are associated with high flow rates, while values in the upper range correspond to the lower flow rates. For m equal 3, that is, under high flow rates, the coefficient K sub 1 is dimensionless, and the sediment transport equation is theoretically based. The water discharge is the sediment concentration is therefore the relation between F and Manning's N is K is equal to 1 in SI units and to 1.486 in US customary units. Therefore, in which K sub 2 is equal to G over K squared. K sub 2 is equal to 9.81 in SI units and 14.568 in US customary units. The Strickler relation for Manning's N is K sub 3 is equal to 0.04169 in SI units with D50 in meters and 0.0342 in US customary units with D50 in feet. Assume that the mean particle diameter D50 is the representative particle size D sub s. Then replacing n squared into the equation for F, replacing F into the equation for C sub s, therefore the sediment concentration is Therefore, the dimensionless lane relation is unlike the original lane relation, which was a proportionality, this new lane relation is a dimensionless equation. Thus, it is properly a sediment transport function. The sediment transport function is it reduces to in which K sub 4, a constant, regardless of the system of units, is a function of K sub 2 and K sub 3. Therefore, the dimensionless sediment transport function is This sediment transport function is applicable in either SI or US customary units. Having assumed m equal 3, the only other parameter to be determined experimentally is K sub 1. Lower values of K sub 1 are associated with higher values of the exponent m. Assume the following example. The application of the sediment transport function leads to